An explosion 2 billion light-years away physically compressed Earth's atmosphere, and most people have no idea it happened. This was not a close call. It was a confirmed measurement, and it revealed just how vulnerable our planet is to the most violent events in the universe, even across distances that should make us invisible. On October 9, 2022, a gamma-ray burst designated GRB 22109A arrived at Earth after traveling approximately 1.9 billion light-years. It was immediately nicknamed the Boat, the brightest of all time. Gamma-ray bursts are the most energetic explosions in the universe, produced when a massive star collapses into a black hole at the end of its life, or when two neutron stars merge. They release more energy in seconds than the Sun will emit over its entire 10 billion-year lifetime, concentrated into a narrow jet of radiation. GRB 22D109A was not just the brightest gamma-ray burst ever recorded. It broke the instruments designed to measure it. NASA's Fermi Gamma-Ray Space Telescope and the Neil Gehrels Swift Observatory both detected the event, but the brightness was so extreme that the detectors saturated. Scientists had to reconstruct the true brightness from instruments that were partially blinded. The afterglow was visible across the electromagnetic spectrum for days and continued to fade over weeks and months. The event released an estimated energy output in gamma rays that is almost beyond comprehension. Research teams published their analysis in journals including Science and Astrophysical Journal Letters through 2023. The isotropic equivalent energy, assuming the radiation went in all directions, was calculated at approximately 10^55 ergs. That number is staggering. For context, a typical core collapse supernova releases about 10^51 ergs of kinetic energy. GRB 22109A outclassed that by 10,000 times in gamma radiation alone. But the most direct, measurable effect on Earth came from a team studying the ionosphere. The ionosphere is a layer of Earth's upper atmosphere between about 60 and 1,000 kilometers altitude, kept ionized by solar radiation. It is the layer that reflects certain radio frequencies back to Earth and enables long-distance radio communication. The ionosphere responds to changes in radiation arriving from the Sun. Solar flares and similar events can cause radio blackouts. What the research team, led by Mirko Piersanti at the University of L'Aquila in Italy and published in Nature Communications in 2023, found was that GRB 22109A caused a measurable disturbance in the ionosphere at depths normally only affected by solar X-ray events. Using data from swarm satellites operated by the European Space Agency and ground-based magnetometers, they detected a change in the electric field of the lower ionosphere within minutes of the gamma-ray burst arrival. The signal matched the timing of the burst precisely. This is the first time a gamma-ray burst has been shown to directly affect Earth's lower ionosphere, a region normally shielded from extragalactic events. The burst was so powerful that even from 1.9 billion light-years away, with virtually all of its radiation absorbed and scattered by the time it reached Earth, enough penetrating gamma radiation remained to ionize the lower atmosphere at altitudes of around 60 kilometers. Now consider what this means for proximity. GRB 22009A was almost 2 billion light-years away. A gamma-ray burst within the Milky Way, pointed toward Earth, could be catastrophic, potentially destroying a significant portion of the ozone layer and exposing the surface to lethal ultraviolet radiation levels. Some researchers have proposed that gamma-ray bursts within a few thousand light-years could have triggered mass extinctions in Earth's geological past, though linking a specific event to a specific extinction remains unconfirmed. The rate of gamma-ray bursts detectable by current instruments is roughly 1 per day across the entire observable universe, though most are billions of light-years away. The Milky Way itself produces few, if any, long gamma-ray bursts relative to star-forming galaxies, but the probability is not zero over geological timescales. GRB 22109A shook our atmosphere from a distance that light takes nearly 2 billion years to cross. The universe does not need to be nearby to reach us. It just needs to be violent enough. Follow for more on cosmic events that connect directly to Earth, and tell me, knowing that an explosion 2 billion light-years away physically altered our atmosphere, Does that change how you think about our planet's safety in this universe?